Okay, Math 170. Now we're going to approach section 1.4, and we're going to start off with describing the tangent problem. So in example 1, we are going to graph f of x equals x squared and find the equation of the tangent line to f of x at the point 1, 1. So before we start, we want to kind of go through what do we really need to know before we start trying to solve this problem. I'm going to piece together a few bits of information from our past. So the first thing I'd like to recall is how do we sketch y equals x squared by hand. I know we can type it in our TI to help us out, but we want to kind of a little bit more accuracy here. So normally what I do with these parent functions is I always like to make a nice XY chart. So I'm going to do that right here. So X and Y. And I have a few of my favorite points. I'll start at X equals 0. So Y is 0 squared, which is 0. I'll plot that right here, 0, 0 to the right. At x equals 1, when we square 1, we also get a 1 back. So that would be 1, 1. Plot that on the right as well. Now, if I plug in -1, that would mean that I'm getting -1, all of that being squared, which in turn comes back out as a +1. So we're going to plot that -1, +1. And I want a few more points just to fill up my graph a little bit more. I'm going to go with 2. So 2 squared is 4. 2, 4 is about right here. And I'll go with -2. And again, remember when I'm squaring, I'm including the negative sign to get a +4. So now we have a few nice guide points to help us out with our sketch. So we'll complete that sketch. Okay, so at least we have the graph. The next thing I want to do is try to understand what do I really mean by tangent line. So I kind of have to go back to my definitions. Sometimes that gets confused with the tangent graph from trig, but we want to talk about tangent line. So just kind of a recall. Tangent lines are lines that intersect the graph in only one point. So I could draw it just to kind of get myself a good idea. So I want to remember that I'm looking at the tangent line at the point 1, 1. So I know that the tangent line has to go through this particular point. And I'll do my best to draw a straight line on this. Normally I'd like to use a straight edge. We'll see if we can improvise here. So if we're going to draw this tangent line, a little shaky, I'm working on it. Take my time. I'd like to have a pretty graph just to make sure. Here we go. Let's try this. Not too bad. Just connect the rest of that. So that is the tangent line. And maybe I'd label that. I'll label that up here just to remember. Oh, sorry about that. Sometimes we switch back and forth between our previous notes. Here we go. Okay, so at least we have the equation of the tangent line, or we're looking for the equation of the tangent line, but we do have a picture. In cases like this, the problem is not too complicated. We could probably guess what we need to know in order to actually find this equation. But in order to develop the calculus behind all of this, we want to go through the cases of, what would happen if we have a more complicated graph? And what happens if we have a different point, maybe not at a clear coordinate or integer 1, 1. So I'm going to need more information. Whenever I'm finding a tangent line, I do know that we do have generic slope-intercept form, y equals mx plus b. Looks like I could probably guess what it is by inspection, but I do need a little bit more information to have a clear idea of what the slope would be. So I'm going to develop this by bringing back a little bit of concept from 1.1 when we're talking about secant lines. So remember with secant lines, just to kind of review, a secant line intersects the graph in 2 points. And I should say at 2 points. So what I'd like to do is maybe choose another point on y equals x squared, not too far away from the original x value that we were dealing with. So let's keep 1, 1. I'm going to kind of mark that in red a little bit. And I'm going to use a nice version. It looks like 2, 4 would be a good one to go with according to our picture. So if I take and actually connect these 2 points, I'm going to have the secant line. My best version of this, if I can. Here we go. Just being real careful. And eventually we're going to show you all the technology behind this. So here we have the secant line. And if you zoom in a little bit, you can see that it does intersect in 2 points, and it looks like there's a little space in between right there. And what I want to really emphasize is we always talk about like what's actually happening at the point 1, 1. And so I'd kind of like to emphasize, maybe I'll put a little box around it, a little purple box. And I'd like you to notice it in that neighborhood. So I'll write that down for you. Notice in the neighborhood of the point 1, 1. If we look at that really closely, and it maybe if we drew these a little bit more accurately, we could kind of see if I can highlight a little bit. If we look really close to the point 1, 1, it appears that the slope of the secant line is close to the slope of the tangent line. So what I'd like to do in the next part is really get a good idea and take an inspection of a few random points along the way. So what I'd like to do is I'm going to play with, let's kind of go through and pick a few points that eventually get closer to the point 1, 1 from the original point we chose, 2, 4, and I'll write that down here. And I know visually we can see on the graph why it's 2, 4, but if we didn't have a nice picture of the graph, we could have plugged it into our function itself. So if you have x equals 2, you could have talked about f of 2 equaling 2 squared. And that's where we're getting our 4 from, just in case the function ends up being a little more complicated and we can't see. And so what I'd like to do is first calculate the slope of the secant line I just drew. That's the red line. So if you remember, slope is the difference. Let's see if I can, I'll do this in purple. The slope is the differences of the y values over the differences of the x value. So remember, we're passing through the point 1, 1, and now we're looking at 2, 4. So if we subtract the y values, we should have, I'm going to go with the secant point first. So I'll look at 4 minus 1, differences of the y's, over the differences of the corresponding x's. So that's going to leave me with 3 over 1. And if we reduce everything, we end up getting the slope is 3. So, okay, yeah, we probably could have figured that out by inspection, but now we have a clear idea of what it's looking like. But I want to develop this a little bit further. I'm going to keep picking points that end up getting a little closer to 1, 1. So maybe I'll take this with the x values here. Remember, if we're trying to get a value that's close to 1, 1, maybe I'll pick 1.5. That's pretty close to the number 1. But in order for me to understand what is the corresponding y value, I would have to then plug that into the function. And I'll work squeezing this in. I'd have to square 1.5 in order for me to find that corresponding y value. And so here I'd probably use my calculator. I mean, I could do this by hand, but we have a lot more concepts to go over than focusing on decimal multiplication. So we do get 2.25 as the corresponding y value. So I'd like to continue to find the slope of this point that I just found in comparison of the line that goes through 1, 1 and 1.5, 2.25. So again, with the slope, we're going to calculate the differences of the y's over the differences of the x's. So I'm starting with the point I just wrote down. I have 2.25 minus 1 over 1.5 minus 1. And a little bit of computation, I should have a 1.25 over 0.5. And here's where we probably will use our calculator again to find that the slope of this line through these 2 points would be 2.5. So that's a second approximation, or the second approximation. And so now, I mean, I can keep getting closer. I really want to stop messing around. I want to get really close to 1. So maybe I'll go even further. 1.5 was about halfway in between 1 and 2. Let's do 1.1. And if I want to find my corresponding y value, what happens if I square 1.1? I should get 1.21. You can test that out on your TI if you'd like. And if we keep calculating the slope, differences of the y's, and remember, we're always corresponding back to the point 1, 1. Differences of the y's over the differences of the x's. We're going to get ourselves 0.21 over 0.1. And if I do the division, I should get 2.1. So there's my third approximation. And so I went from 3 to 2.5 to 2.1. And maybe I want to take it from the other side of x. So here I was dealing with positive, well, I should say values to the right. And see if I can mark this on the graph so we all see. So again, if I was looking at the x value 1, the first few values that we found, we looked at what happens at 1.5. And we calculated its corresponding y value and found the slope between that and 1, 1. Then we went really close to 1 I don't know if we can even see it as we mark it, but it's about 1.1, right next to the 1. Find its corresponding y value, which is really close to 1, 1, and calculate the slope of the secant between those points. So that's really close to 1, 1. So I want to take it from the other side. I want to see what happens, and maybe I'll go in orange. I don't know if it's a little hard to see here. But let's look at what's happening on the left side of the number 1. So let's say, you know, instead of, we're not going to go through 0.5, let's get really close. Let's go to 0.9. So again, you're barely right next to the number 1 on the left side. So let's look at that, 0.9. And again, if I wanted to find its corresponding y value, whoops. I do want to actually plug it into the function. Don't get mixed up there. So 0.9 square. So that's going to give me 0.81. So now if I find the slope of the line through that point and 1, 1, we can calculate it. And I know we have ways to do this a little bit faster, but I'd like to write it out just to emphasize what we're actually doing each time. So the differences of the y's over the differences of the x's. And if I subtract, this time I get a negative numerator, about 0.19 over negative 0.1. And of course, if I use my calculator for the division, negative divided by negative gives me positive, and then my calculator will give me 1.9. So that's looking at the slope of the line through those 2 points. And even better, if I want to get really, really close, this would be me really exploding the graph, and maybe even getting beyond the 1.9 and maybe go to 1.99. Find the corresponding y value where it hits the function and draw the line through those 2 points in relation to 1, 1. I'll shrink it back down for you all. So maybe I do want to do that. Let's see. 0.99. We are really close to the value of x equals 1. And if I were to find the corresponding y value, actually I want to leave myself a little more room on the right side or left side. 0.99. If I square 0.99, I should get 0.9801. And again, if we take the time and do the computation of the slope, differences of the y's over the differences of the x's, I'm going to get a negative y value in the numerator, 0.0199. And in the denominator, I get negative 0.01. And if we do the math, we get positive and we get 1.99. And so if we're looking at this, you can kind of play with this and say, all right, well, if we approach, and I don't know if I'll draw a little bit of highlighters. The first few values, I tried to approach the 0.1, 1 from the right side. So as I was picking points from the right side and finding the corresponding y values and calculating the slope of the secant line, I'll scroll down. I went from 2.5 to 2.1. And then if I'm looking at the left side, so if I was picking values a little bit to the left of x equals 1, and again, getting really close, finding the corresponding y value, calculating the slope between that line, we're noticing that we are getting values. We're actually getting values that are pretty close to a nice integer. And you can probably guess, based on the function that we drew, the slope of the secant line seems to be approaching, and I'll pause so you guys can think about it. And if we're looking at this a little carefully, I'm kind of seeing from these values, the slope of the secant line seems to be approaching 2. And therefore, you can conclude that the slope of the tangent line is, in fact, 2. The idea is to get the points so close that they're on top of each other so that they end up being the slope of the tangent line. So we can do this through inspection. And I can then go through the algebra to find this, but in chapter 2, we're gonna have a much nicer way for us to give us the slope of the tangent line with a lot more certainty. Right now we're guessing. We could be off a little bit, but I did pick a function that it ends up actually being quite nice. But again, you know, what do we do when we have this issue? Now, just be careful. You know, I got excited and almost moved on, but we have to think when we are trying to figure out what the equation of the tangent line is, they asked for equation. They didn't just ask for the slope. So I also want to remind myself, the problem was asking for the equation of the tangent line. So if we kind of have a recall for us, if we were looking for the equation, I'll write this up to the side. Remember, we already have the slope is equal to 2. And we are actually looking to go, let's see, we're going through the point 1, 1. According to the directions. So if we were to, I'm gonna use the point slope form, y minus y1 equals slope times x minus x1. That's the fastest way for me to get the equation. I have y minus 1 equals 2 times x minus 1. And then if I were to simplify it, a lot of times we love to see this in slope-intercept form. So we distribute the 2 through. We end up solving for y by adding 1 on each side. And we get y equals 2x. Now, -2 plus 1 is minus 1, or -1. So that should be the equation of the tangent line. So we can inspect this on a TI, because that's the tool that we actually have in our hands. And then I'll show you a little bit on Desmos as to what's actually happening. So let me share that with you all. So let's do a quick graph of y equals x squared. Let's choose that x. We'll square it. And then let's also draw the tangent line as y equals 2x minus 1. And I know I have a standard viewing window. It should help a little bit, and it does appear that we have the tangent line. And we can zoom in, or zoom in really close to it if we want to. So let me see if I can do that with you to inspect that. So item number 2, if I press zoom, and actually, again, if you look at the neighborhood of the point 1, 1, we could keep zooming in closer and closer and closer until there's a point where eventually we can't tell the difference between the function itself and the line. So I don't know if you're kind of seeing where that red drops off. So that's something kind of we're looking to do as we're going through this process. So let me see if I can show you on Desmos. This is going to be the key to a lot of these problems. So let me see if I can share with you right now. Let's pull up. I have a secant line function, and maybe I'll include the link on this for 1.4 to make sure that you guys can play with it yourselves, because you can these are kind of much nicer versions where you can interact with these. So now you're looking at the graph again of y equals x squared and the slope of the secant line, or the actual function at the secant line. And what we're trying to understand is what happens when we bring these points so close, or we take this point 2, 4, and we drag it so that the points get closer and closer and closer. So eventually the secant line only passes through one point, which then it becomes the tangent line. So kind of you can see an animation. And again, you can take this with any point on the function as long as you're dragging it back and forth. We can exaggerate. So secant line, picking values of x that are closer and closer and closer and closer to the actual point in question until we get a tangent line. So it's really, really neat to see, visualize, and make sure that the function actually comes to life. So you can play around, and we can also go through. But the question will be later that, you know, we're not going to have these nice parent functions. Let's see if I can go back to our notes here. The question will end up being, you know, what happens when the functions get more complicated? And maybe the points are something that we can't visualize. We have to really use a graphing tool to help us understand this. Well, the answer to this is the technique is going to involve finding limits. And so that's something, a little sneak preview of the next section. So stay tuned for that. So just an application coming up with example 2. We're going to look at the velocity problem. So nice applications of slopes of tangents. And just kind of bringing a little bit of knowledge back from your past. We have a table showing the position of a cyclist. And so what happens if we have T standing for the time in seconds and S standing for the meters, then what we're kind of looking for is, you know, part A, what's the average speed after 3 seconds? B, how fast was the cyclist going at time equals 3 seconds? And then we can kind of develop what the answers to these questions are. So if we're looking for the average speed after 3 seconds, I'll have you recall in algebra. And actually, we're switching on accident. Let's move around. We're looking at recall. So in algebra, if we were going to calculate the average speed, we would have rate times time equals distance. And so if we were to solve for rate, speed, rate, average, we're going to get R equals distance divided by time. And if we're looking at 3 seconds, I'm looking at T equals 3, S equals 10.7. So I can plug that in. Distance is 10.5 meters. And time is 3 seconds. And then if we were to use our calculator, we should have 3.6 meters per second. So that's the average speed after 3 seconds. Now, kind of, you got to make sure when we're going through these, talking about average speed versus instantaneous velocity, we'll get that in a little bit. The cyclist was not going 3.6 meters per second the entire time. Sometimes they had to slow down. Could be wind resistance, could have hit a rock, could have had to stop for a little bit to let someone cross. So this is just the average as we go. Kind of think about it as when you encounter traffic. There's a certain set distance from your house to Cerritos College if we were going back on campus. And you kind of have an estimate of how long it takes you each time. But sometimes things vary. So, you know, whether you leave your home and you're a little further away, and maybe there's not so much traffic, and as soon as you get a little closer, there's a bunch of traffic. There's an average speed going on based on this. So what we want to deal with is kind of look at, you know, what's actually happening exactly at time equals 3 seconds. And so they want to talk about the instantaneous velocity. And here, algebra is not answering this question. The idea to talk about instantaneous velocity, and I'll write this down, it's nice to note. The idea behind this is we want to approximate the instantaneous velocity using average velocity from the data we have. And now some of you are kind of looking at this data that we have and you're thinking, ordered pairs. And that might bring back some memories from example 1. And that's actually what we're going to be looking at. So what I'm going to, I'll note this as well. It's important to write down. We're going to compute the average between 2 points and then take the average of that. A little bit more averagey, so we should say. So what I'd like to do is divide distance by time. So I want to talk about the average velocity. I'll do this in 2 places. Let's see. So average velocity, I'll write this in green. So I'm going to look at the average velocity between time equals 2 seconds and time equals 3 seconds. So if I go back, and I'm getting pretty much a point, 2 points that are close to the number 3. So we're looking at 2 and 3. Let me write that down a little more formally. T equals 2 and T equals 3. So I'm going to look at distance divided by time. And if we're actually talking about what's happening between those 2 points, well, between the distance for time at 2 seconds and the time at 3 seconds, we're looking at 10.7, take away 5.1. So what's happening at 3 seconds? 10.7. 2 seconds, 5.1. And then we're subtracting off the seconds. So we should have 3 minus 2. So distance over time. Now do the math, a little computation for us. We should have 5.6 over 1. And if we're looking at trying to get units involved, remember that we have meters on top, seconds on the bottom. So we should have 5.6 meters per second. So we'll do the same thing. I'll pick orange on this one. I'm going to do this to the other point next to 3. So I'm looking at 3, 10.7, and 4, 17.7. So I'm going to take the average velocity between t equals 3 and t equals 4. So we're going to do the same thing. We're going to have our distance over time. And I'm going to use the distance for 4 seconds first. I have 17.7. Subtract off the distance at 3 seconds. And so then we have 4 minus 3 in the denominator. And again, we're at meters and seconds, just so that we're clear. So that's going to give me 7 over 1. And again, if we're really clear about our units, we should have 7 meters per second. So we just found the average velocity between the two data points, 2, 5.1, 3, 10.7, and then another average velocity calculation between 3, 10.7, and 4, 17.7. And if you're kind of recognizing that we're taking the differences of the distances over the differences of the times, should bring back a little bit of memory of something about like differences of y's over differences of x's. So think about that. But we have two averages going on. You know, why don't we try to be a little bit more precise, and maybe now let's try to take the average here. Let's take the average of these two. And so our best estimate and again, we're estimating, of the instantaneous velocity at time equals 3 seconds is actually the average of the two velocities we computed. So if I wanted to write that out, let me see if I can move to the side a little bit. I'm going to use function notation, v of 3, and there's an approximation. So I'm looking at averages 5.6 plus 7 over 2. And if I can, see if I find 5.6 plus 7 over 2. If we just do the math, we're in calculus, we can skip a few steps. That should leave us with 6.3 meters per second. Now, in a few sections, we're going to formalize this process, but it's kind of important to realize what are we actually doing when we're taking averages closer and closer and closer to the point in question. So I'm just going to summarize a little fill in the blank here. Remember, we're approximating the instantaneous velocity by computing the average velocity. And eventually, a little note to kind of keep in mind is that if we're talking about instantaneous, a lot of times people like to refer to this as the slope of the tangent line. And when we're talking about average velocity, a lot of times we can generalize this to slope of the secant line. Sometimes it's a little harder to tell when we're in table form and we don't see X's and Y's going on, but this is what we're actually doing. We can actually call T, time equals X, S, meters equals Y, and we could kind of realize we're actually doing the same sort of idea that we were dealing with in example 1, except we took it a little bit faster and took the averages of the averages, just to get a little bit closer. So again, we're going to formalize this in the next section. So, well, maybe a couple sections from now, but nevertheless, I'll see you then.